can teach us three main things. First and foremost is what I like to call the hard science, which is investigating things such as solar system formation theories, which, for example, Rosetta looked at a lot. Secondly, we can use it to validate planetary defense strategies, which is something that the ADA mission is looking at, which you may have seen earlier this afternoon. And finally, as a more exotic application, we can explore small bodies to look at in situ resource utilization techniques. And so we can do all these three things using simply an orbiting mission, but we can significantly increase the mission return of one of these missions by including lander and indoor planetary, indoor surface mobility operations. But unfortunately, as shown by the Minerva lander, which failed to reach the surface after being released from the Hayabusa spacecraft, as well as Philae, which bounced around quite a bit, we saw that the delivery and the operations of these craft can be quite challenging. And so in order to properly design such spacecraft, we want to be able to do high fidelity simulations of lander and rover spacecraft on small bodies. And so that's really the focus of my talk today. I want to talk to you about how to go about doing these simulations and some of the analytical work that we did behind all of this. So just as a quick outline, I'll show you the main elements that go into these simulations, show some sample applications where we vary the lander shape and the number of rocks on the surface of a small body and look at the effects, and then discuss our work on the liftoff velocity. So in order to do high fidelity small body lander simulations, all you need is three main modules. The first of this is the gravity module. So we model the complex gravitational field of a small body using the constant density polyhedron model. And we use a reduced resolution shape model to make this model numerically feasible. And we also linearize the gravity field. Secondly, there is the surface module, which mainly serves to detect collisions between a lander and the small body surface, where we use these local worlds that you can see here that basically subdivide the whole asteroid surface and procedurally generate rocks on the surface. And then finally, there is the actual collision handling module, which takes into account the restitution and friction effects that happen during a collision of a lander with the surface. So as an example of what we can do with this simulation software, I'm showing a sample simulation here of a cube-shaped lander deploying to asteroid Itokawa. The playback speed changes during the video, and so you can see it descending. And you can see the procedural generation of the rocks going on right there. And so the lander does a couple hops before it will eventually come to a full rest. And so one of the main applications of this software isn't just making cool videos, but lies in running thousands of these simulations where we vary the initial conditions such as the release position, release velocity of these landers, and that way you can effectively validate a deployment strategy that you might design for one of these landers. So we see it settling there. And similarly, we can also vary the parameters of the surface, such as the coefficient of restitution, and investigate the effects on the lander. And so you see here the actual trajectory that the lander followed as it descended towards the surface. So I mentioned those applications. We can also simulate surface mobility operations. But so specifically what I'm going to look at in a minute is a variation of the actual shape of these landers and the number of rocks on the surface. And just briefly, in future work, what we plan to add to this software is actual sustained contact motion for one of these landers, as well as some model of the surface compliance, such as the example you can see here, some work done by my colleague Paul. And so we can ask ourselves, okay, if we have some set of instruments, a given mass, a given density, doesn't matter how we package these up, what shape, hull you put these in. And so one thing we did was we took these 5 shapes, sphere, icosahedron, a cube, tetrahedron, and a 3U CubeSat shape that I call beam, and run simulations, about 500, where we give all of them the same initial conditions and look at the way these things fly and bounce around and settle on the surface. And so I'll show a very quick demo here where we see 4 of these shapes flying around, very nice. But let's keep going. So what we can generate is this plot of the distribution of the settling time of these 5 shapes. And so I've ordered them here in order of low inertia to high inertia. And so what we can very clearly see is that the shapes with a higher inertia settle faster on the surface. And effectively what this says is that if you look at the shapes and the inertias, is that the more distended a shape becomes from a sphere, the quicker it will settle on the surface. And this is due to the way the normal and the friction force act during the collisions, which are the main energy dissipation mechanism for one of these landers. And similarly, if we look at the surface dispersion of these objects, which you can see on the right here, we can see that the final settling locations of the simulations of that beam, which are shown in orange there, are much more clustered than that of the icosahedron, which makes sense since, you know, if an object spends less time bouncing around, flying around, then obviously it tends to be more, the final positions will tend to be more clustered. And this effect is more pronounced for high coefficient of restitution E. Similarly, we can vary the number of rocks on the surface. So rock density is what we call that, which is parameterized by this rock number K here. So you can see some examples of how it actually looks on the surface when we vary this number. And so interestingly, we find that for the beam, so the one shown on the top here, the rocks have a very minor effect. So whether there's no rocks on the surface or a lot of rocks, it only very slightly affects the settling time of these landers. However, for a more spherical object like an icosahedron, the effect becomes quite distinguishable. And the reason this is different is, again, due to the difference in shape for these objects. We find that objects that are more spherical are affected by the rocks much more strongly. And so, as I said, we were trying to start implementing the contact motion, you know, where one of these objects is really kind of rolling around on the surface. As we were thinking about this from the point of surface mobility operations, we asked ourselves the question of, okay, if we make these things move around, what kind of speed roughly should we be giving them? And so this got us to think about the concept of the liftoff velocity. So imagine, if you will, for a second that you are in I'm gonna stand like this, that's much easier. If you're an astronaut running around really on a small asteroid, how fast do you need to run for you to lift off from the surface and basically, you know, start following that surface curvature? If it's a, you know, just a circular asteroid, this is very easy. It's just a circular orbital velocity, this expression here. Now, if the thing is rotating, you get a bias from the rotational velocity of the surface, depending on whether you run with or against the velocity. Still pretty easy. But in that final case where, you know, the shape is no longer circular or you're running in some weird direction, the answer is not that obvious anymore. So we show some example values there for a 1 kilometer radius asteroid, this on the order of a meter per second. But basically, this led us to derive this expression for the liftoff velocity, which is shown as semi-complicated on there. But the most important thing is that it uses this factor rho, which is the surface curvature of your target. And we also see a plus-minus factor here, which is that directionality bias that I mentioned. And so as an example, we can apply this to asteroid KW4 alpha and produce a distribution of the minimum and the maximum liftoff velocity that is encountered at each point on the surface as a function of, you know, which direction along 360 degrees you locally sort of move in. And so we find that the velocity is very small at the equatorial ridge, and this is because KW4 alpha is a fast rotator, meaning that its equatorial ridge rotates at near orbital velocities, so very little additional velocity is needed for a particle to reach that orbital velocity. But in general, we find liftoff velocities on the order of 0.1 to 2 meters per second. Second sort of criterion we can define is that which we call the ridge liftoff velocity, which instead of really following that large surface curvature of an object, it's defined when something moves on a very small ridge or asperity. And in this case, the object will lift off for a very short amount of time and pretty much very shortly again impact the surface. This velocity is of a much lower order. For something, you know, with a wheel on the order of 10 centimeters, this velocity is only about half a centimeter per second. For something bigger, like an astronaut walking around, where you would use a radius of 1 meter, it's more on the order of 2 centimeters per second. And so this velocity has implications with regards to friction, because basically imagine if something is rolling on a very rough surface. It means that once you exceed this velocity, your particle or rover or whatever will basically be doing very brief hops. So it will no longer be in continuous contact with the surface. So you would expect the friction to be slightly different. This velocity also has some geophysical applications. For example, here I'm showing the lines of the latitude of minimum release. Basically, due to the dynamical environment on KW4, any particle that's near the poles will naturally tend to move downwards towards the equatorial ridge and naturally gain velocity. And then we can ask ourselves, well, okay, if we know these objects will be moving down, gaining velocity, what is the latitude from which, the minimum latitude from which something must have come if we know that it lifted off when it reached that equator? And so we show those lines on the right here for a few different values of the coefficient of friction. And effectively what this shows is that it's very difficult to do much surface exploration on KW4 because from the most regions from which you would start doing your surface exploration tend to naturally push you towards the equator and will throw your lander into orbit. Similarly, we can show these figures of Phobos where we again look at the minimum and the maximum liftoff velocity here on the order of 2 to 5 meters per second, which if you were at the Phobos Demos conference earlier, you may remember that probably for an astronaut moving around on the surface would be around half to 1 meter per second. So that's nice because these limits are above that practical velocity we would use. However, more interestingly, if we look at that ridge liftoff velocity, for an astronaut, radius 1 meter roughly, that velocity is on the order of 3 meters per second. For a wheeled vehicle, it's about 1 centimeter per second. So we can expect that when we exceed these limits, we will see some changes in the friction and therefore also the traction that a vehicle experiences or exerts on the surface. So in conclusion, I've shown that the dynamics of something moving around or on the surface of a small body is challenging. I've shown the elements that are needed to do high fidelity simulations of the motion of these things, which we can use to validate the deployment strategy. And we also investigated the shape of these landers and the number of rocks on the surface, from which we concluded that they very strongly affect the motion of these objects. Secondly, we started looking into the contact motion of a lander or a particle on the surface, and in this low velocity regime that's present on these small bodies, we showed that there's some interesting speed limits that apply to surface exploration vehicles. And these limits have some interesting geophysical applications as well. And with that, I'll take any questions. Thank you.
Nice talk. Can you tell us a little bit more about that coefficient of restitution?
Yeah. So effectively, that coefficient of restitution that sort of tells you how much of the normal velocity is damped in a collision. So if you just think of a simple basketball bouncing, it just tells you if you have some incoming velocity, what is the ratio to the outgoing velocity. For an arbitrary shaped object, it's a little bit more involved, but that's the essentials.
Hi. Hello. Yes. So the coefficient restitution of 0 is sticking and 1 is elastic. But nice talk. Can the CubeSat actually map the gravity field as it bounces around?
You could get some information, but I would think that it's quite difficult. If you're thinking, it kind of depends on what gravity field model you're using. Because of the arbitrary shape of these bodies, I think it would be difficult to really get some global sense. You could get some local measurements that you could then maybe combine with measurements that an orbiter takes, and that would probably give you some extra information. But I think it's quite limited what you can measure with just a little cube bouncing.
I wonder if you're I wonder if you're aware of the Soviet failed Phobos mission that was going to have these landers that were basically bowling balls with a stick out that could sort of spring themselves around randomly around Phobos. It didn't get, it got close to Phobos, took one picture, and then the whole spacecraft failed. But I wonder if you could learn something about what you would like to have as far as mobility on a small object, like some kind of more insect-like hopping around rather than attempting to crawl and stuff like that.
Right. Yeah. So actually, the person presenting after me, Ben, right there, he will talk about that quite a bit. So I think I will leave that to him. And if you still have questions after his talk, I suggest you ask him. Thank you.
Thanks. So that was